Hi. Sometimes we have more than one variable. For example, when we sample at same location more than one attribute of the soil, the forest, water, etc. And you are interested to analyze how those variables are related. For example, if the porosity of a soil is directly related with the amount of a given pollutant concentration, or if the temperature or humidity of a given region is related with the number of forest fires occurred in the same region. In this third part, we'll see some statistical tools to describe the way two variables are related. Now, when you try to summarize a relationship between two variables, it is important to follow the principle of maximum parsimony. If a simple solution fits your problem, avoid the complicated solution. Now, the set of tools of this practice is called regression analysis. And we are going to see here only the linear regression. More precisely, we are going to see how and when we must use simple functions with minimum number of parameters, preferentially linked to the physical phenomena. I'm not going to talk about the mathematical framework of the linear regression analysis, but only how and when we can apply it in the framework of exploratory data analysis. Remember, even a simple tool like fitting a cloud of points with a straight line becomes useless, a useless exercise if you do not know the purpose and the limits of it. Today we'll talk about some simple statistical tools to characterize joint behavior of several variables. Let us come back to the contaminated site of previous model. From the wells, it is very common to measure more than one property in each sample, but we'll talk about the relationship between two variables, the Bivariate Analysis. This is raw data coming from the sampling campaign. We have several variables representing the properties of the soil and the contaminant concentration. We intend to evaluate the relationship between, for example, the porosity and the pollutant concentration, or porosity and permeability, or to know how one property is related with the spatial domain, for example, how the pollutant concentration is distributed in depth. Suppose the two arrays of data, the permeability and porosity. One of the richest ways to describe the relationship between those two variables is through a bivariate diagram, or what you call a B-plot, where the permeability values are represented in horizontal x and the porosity values are represented in vertical x. Each point represents one pair of those variables, which are the coordinates of the points in the graph. This is another example. The shape of the B-plot can show us a good direct relationship, like this one, where the values of both variables increase or decrease together, or a good but inverse relationship when one variable increases and the other decreases, or no relationship at all. It means that no matter the values we take from the first variable, the second variable can have any value. There is no increasing or decreasing trend. With the B-plot, we can visualize if the relationship of two variables is constant for the entire range of values, or, like in this case, we can have two subpopulations with different behaviors, one with a good relation, linear relation, and the other with almost no relationship between the variables. Another example, where we can differentiate from the global population two eventual subpopulations with totally different behavior. Now, if we represent all points values in the porosity X by classes we obtain the marginal histogram of porosity. The same for the permeability X, where we obtain the marginal histogram of permeability. Now, dividing the B plot in classes like those classes here, we can calculate the absolute frequency of each class, giving rise to what we call a bivariate histogram. From the B histograms, we can extract one very rich tool to describe two variables, the conditional histogram. Here we have the histogram of variable 2 in the class 5 of variable 1. This is called the distribution of V2 condition to V1 equal 5. Here we have the histogram of variable 1 in the class 1 of variable 2. This is called the distribution of V1 condition to V2 equal 1. In this way, we can explore the behavior of one variable in no domain of the other. We can also have bivariate analysis with categorical variables. For example, the porosity distribution in two types of soil of the same population. A deep sand with lower values of porosity, let's say sand A, and a superficial sand with a very high porosity, sand B. Here is the histogram of porosity, and we can extract from this histogram the conditional distribution of porosity of sand A, which is distribution of porosity knowing the sample belongs to sand A, and the conditional histogram of porosity knowing the sample belongs to sand B. Let us see another representation of the bivariate diagram. If we create classes of one variable, we can represent the values inside that class in terms of the medium, quartiles, maximum and minimum of those classes, the B plot. Suppose we divide the porosity range of values in 5 classes, and we take, for example, the first class, and we can calculate for this first class of porosity the minimum, the maximum, medium, quartiles of permeability, the second variable. And you can represent it by the box plot of permeability values of first class of porosity. Let's see the second class of porosity, and here you have the third class, the box plots of permeability for the total number of classes of porosity. Now we'll talk about some simple statistical tools to characterize the joint behavior of several variables. This is called linear regression or simple linear regression, to differentiate from the multiple linear regression when we have more than 2 variables. Linear regression summarizes the behavior between the 2 variables through a best fit line, the more representative line of the cloud of points. In this case, we have 2 variables, porosity and the permeability. And in X we have the permeability, which is regarded as the predictor, the explanatory or independent variable. And in Y, X, we have the response or the dependent variable. The mathematical expression here of the line contains the two variables. For example, in this case, we have the permeability as the independent variable and porosity as the dependent variable. The best fit line must be representative of the cloud of points in order the equation makes sense as a dependency descriptor of both variables. We're not going to detail the mathematics of how to get the best fit. For this purpose, you can have a look to Khan Academy video lessons, those ones here. Instead, we are going to see how and when we apply the linear regression to explain the dependency of the two variables. For example, here in this case, we can use the linear regression to explain different local bivariate behaviors of the intervenient variables as a pattern recognition tool. This is in this case we are interested to see the relationship between the droughts, extreme lack of precipitation, and along the time in different regions of Portugal. This is the north, the center, and the south. Here, the linear regression is used as a classification tool to differentiate the different regions according to susceptibility to drought. Or we can use a linear regression model as a predictor. Let us come back to our example with a set of sample values where we wish to infer a bivariate relationship but valid for the entire region. Bivariate linear regression model as a predictor means that we wish to infer a model that is able to predict the dependent variable in new situations where we just know the independent variable. In this case, we usually work with two datasets. The first one is the training dataset, composed by samples we use to infer the behavior of the two variables by a good fit to a linear function. The second data is validation dataset, composed by samples that were not used in this first step of training. With the validation dataset, we test the bivariate relationship model we found in this previous step with the training data. Now, once we get the model that fits satisfactorily the validation dataset, we must assume the model valid for the entire region of study, the unsampled location. This is an assumption regarding the stationarity model for the entire region. Let us see a simple example. Suppose the following set of 500 data of porosity and permeability. And we divide into two sets. The first training data set with the first 100 data where we fit the linear regression model. And validation data set with the complementary 400 data where I test the linear regression model calculated with training set. With the training data set, we infer the best linear regression, this one here. With the second validation data set, we can see how good was the inference of this first step. Now we can see the red line of the model obtained here with the training, and the green model obtained with the validation data set. We can see that the difference between the predictor and the regression of the test data is minimum. And in this case, we could consider the linear regression model with acceptable predictive accuracy. But we can also compute the residuals, which are the difference between the predicted value by the model, this one, yeah, and the real data of the dependent variable of the validation dataset. This is the another residuals, etc. And there are plenty of statistics that we can compute with the residuals to measure the goodness of the model for the validation dataset. Just one word about the regression exercise. Suppose instead the linear model we adopt a more complex non-linear polynomial regression, this one here. One can see this regression function fits much better this data set, the training data set. But look what happens when we try to apply to the test data set, which non-linear best fit is totally different model, the green one, from the red. It means that, in short, in the first step, there is what we call a clear overfitting of the training data set. It fits well the training data, but with no ability to predict any other data. It cannot be used as a predictor for the unknown permeability values. Here it comes the maximum parsimony principle we should apply in these cases. Simple models are preferable to more complex ones just because they are more testable and more easy to be associated to the physical phenomena. We have seen how appropriate is the feed to the available data set, but at the end of the day, we must go back to the physical phenomena and analyze how the feed is compatible to the physical phenomena which is behind sample data. This means to analyze the spatial representativeness of the data, spatial homogeneity or spatial stationarity of main statistic, etc. Something that we'll see afterwards. To summarize those bivariate diagrams, the B-plots between two variables, we can have some statistical measurements of the correlation between two variables. This is the covariance, or centered covariance of a discrete set of data. It describes the degree to which the two variables tend to deviate from their respective mean in similar ways. If we standardize the covariance, the centered covariance, by the standard deviations of the two variables, we obtain what we call correlation coefficient, also known by Pearson correlation coefficient. If the square of this correlation coefficient is no else than the coefficient of determination. Some remarks about correlation coefficient. The correlation coefficient ranks from the maximum +1 to a minimum value -1. This is an example of a very good direct correlation coefficient where the variables are positively correlated, 0.71. And this is an example here of a good but inverse correlation coefficient where variables are inversely correlated. When one increases, the other decreases. Or a very low correlation coefficient, close to 0, which means that the variables are not correlated at all. Last note, the correlation coefficient is extremely sensitive to points which are located far from the main cloud. Take this example. These two variables have no correlation at all, 0.11. Let us add just one more point, this one here, and the correlation coefficient jumps almost to the maximum value, 0.99. Of course, this is a fake correlation coefficient measure, exactly because it's extremely sensitive to points which are located far from the main cloud. In short, the correlation coefficients must always be analyzed together with the representation of the cloud of the point. Let us recap. Univariate and bivariate statistics should reflect the most relevant patterns of the data, should explain the main relationship between data, should always focus on the maximum parsimony principle. Just simple theories are preferable to more complex ones just because they are more testable. And finally, the use of statistics to summarize the behavior of key variables must be balanced against the drawbacks to condensed information, sensitive to extreme values, limited description in the case of bivariate, etc.